All right. So yesterday we started sort of what I call the differential calculus, and we talked about this thing called the derivative. So if we have a function y equals f of x, so it looks like this, and we look at a particular point on the graph, a comma f of a, we notice that on some graphs, if you zoom in far enough, even though globally it looks like a curve, if you zoom in, it's going to look like a what? A line. And in that case, we call such functions differentiable. And the slope of this line that we call the tangent line is what we called f prime of a. That was the derivative. Okay? So f of a, that was the y value on the graph. F prime of a was the slope. And we had two different limit definitions of derivative. They were equivalent, and hopefully you took the time to watch those videos to give you extra practice. But one of the definitions of derivative, f prime of x is the limit as h approaches 0 of f prime of a. We haven't done the x yet. That's the next slide. Okay. And once again, to remind you what's going on here, and I always encourage students to always have a picture of what's going on. Try to make it a better picture. Is what this is a slope. Because this is a slope. This slope is the slope between 2 points on the curve. So that was what we called the slope of the secant line. Okay, so that's slope of the secant line. And then what we do is by letting h go to 0, we're moving these 2 points together. And then what happens is that as we move these 2 points together, that secant line becomes the tangent line. All right? And I had a little animation on Desmos that actually showed you that. Okay? So once again, when you're working through these calculations, you're working with slopes. Slope, slope, slope. AKA rate of change. So are there any questions on the concept of derivative, what it's trying to tell us? And so yesterday in section 3.1, we were finding derivatives at particular values. Here's a function. What's the derivative at 5? What's the equation of the tangent line at 5? You follow? We always had the derivative at a particular value, a. So what we're going to do today is say, okay, well, what if I wanted a formula for the slope at any value x? So just like f of x is a formula that gives me the y values on the graph, I want a function that gives me the slope at any point on the graph. I want f prime of x. So I want the derivative itself as a function of x. And so all we need to do is replace the a here with the x. So it's a syntactic change. But for us, it signals to us that now we're going to have a function that will give us the slope at any value x. And so that's the definition here. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h for all values x for which this limit exists. And today we will have a discussion at the end of class about where things don't work on the derivative. Okay? So once again, f of x, this gives you the y values. outputs. F prime of x, this is going to give you the slopes or rate of change. So we start off with a classic x squared. Find a formula for f prime of x. So f prime of x, by definition, that's the limit, as h goes to 0 of f of x plus h minus f of x, all divided by h. Now once again, on the test, on the take-home, if I want you to use the limit definition of derivative, I will tell you, and I will tell you which limit definition to use. You follow? I mean, it'll be very explicit. I want you to use the derivative. I want you to find it this way. Okay? Now, once again, we've got to do some algebra work here. I need to know how to get the f of x plus h. So once again, either literally or in your mind's eye, everywhere you see an x in the formula for f of x, you want to envelop it in parentheses, erase the x, replace it with x plus h. So we're taking the x plus the h first, and then we're squaring it. You follow? So once again, f of x plus h is x plus h quantity squared, and we want to simplify that. When in doubt, write it out. X plus h quantity squared really means I want x plus h times what? X plus h. So x times x is x squared. We'd have an x times h plus another x times h. That gives us how many xh's? 2 xh's. And then h times h is h squared. Okay, so you make your smiley face, you call it FOIL. It's distributive property, but everything gets multiplied by everything else, and you add them all up. So this is the correct expression for x plus h. And just as a warning, f of x plus h is different than f of x plus h. The most common mistake I see in these kinds of things is if the f of x is x squared, they think of f of x plus h as being x squared plus h. That is incorrect. Here we're adding the x and h together and then plugging it into the function. Here we're taking the function first and then adding the h. You see the difference? All right? It's like when you're baking a cake. This is the example I use in college algebra. When you're baking a cake, adding the egg before you bake the cake is a drastically different result than adding the egg after you've baked the cake. You follow? So when you have this in parentheses, you're adding the h first, then moving it into the function. All right? So be on the lookout for this. So, back to our problem then. We're asked to find the derivative. What we need to do is now we need to substitute expressions in for these things. So once again, every time you substitute in math class, go ahead and use parentheses. So f of x plus h, I know that. I'm going to put in the quantity here. X squared plus 2xh plus h squared. Minus my formula for f of x, x squared over h. And you want to use parentheses. Now in this case, there's only one x squared here. There's only one term, so the negative just applies to the one term. So we can go ahead and drop those parentheses. And you can see what's going to happen to the x squareds. They're going to cancel out. And what's left over, I'm hoping I can factor an h out because I'd like to cancel that h from the denominator. So sure enough, look at the numerator. What's in common to both terms? H. So what can I do with this h? Cancel it out. Now, unlike before, plugging in h would give us a 0 in the denominator. Do I have any challenges plugging h equals 0 in now? No. What do I get? 2x. So the long and short of it is, for f of x equals x squared, f prime of x is 2x. So x squared tells me how far up the y-axis to go. 2x tells me what the slope's going to be. You follow or not? Okay. So let's fire up Desmos here. And I'm going to show you something. Desmos will numerically calculate the derivative as long as you're using x as your variable. So if the problem gives you like a t or a y or a theta, just when you plug it into Desmos, call it x. It'll actually compute f prime of x and graph it, and then you can check your answers. What did we get for our answer? We got 2x. Let's check it. So that's what the derivative should be. That's what we got for our answer. Do you see how they're the same? So you can graphically check your answers to derivatives on Desmos. This is why Desmos is such a great tool for you to have. Because you may check the answer in the back of the book, and it may not look like what you have, but it might just be that they've done a lot of fancy algebra that you've forgotten how to do. So Desmos is a great way to check graphically. Oh, these graphs line up. We're good to go. Let's take a look at this, and let's do some tangent lines. Right. Jacob, what's your favorite negative number?
With negative 5.
Let's look, okay, negative 5. Let's get the tangent line at negative 5. So what do we know? Tangent line formula, y equals f prime of a times x minus a plus f of a. The a value here is what? I want the tangent line at negative 5. So let's go through here. I've got my f of x. That's x squared. I need f of negative 5. And what's f of negative 5? 25. I need my f prime at negative 5. So let's see. Whoops. My f prime of x is 2x. My f prime at negative 5 would be what? Negative 10. And now I've got everything I need for my tangent line. So y equals negative 10 times the quantity x minus a negative 5. That's really x what? X plus 5 plus f at negative 5, which is 25. And so if I wanted to simplify this, y equals minus 10x. I'd have a minus 50 plus 25, so that's what? Minus 25. Okay. Common mistakes I see here. Make sure you plug the number in not only to the function but also the derivative. Your final answer for tangent lines, you should be able to reduce it to a y equals mx plus b. All right? Common mistake I see with students is they put this here and they forget to plug the negative 5 into the derivative. You follow? So I recommend starting off every single tangent line problem, write this formula down, plug in the actual number where a is, and then do the work over here. You follow? Just keep yourself organized like that and you'll be fine. Now, what's the ultimate check? If I graph the function where x equals 5, and I graph the tangent line near x equals 5, when I look at their graphs, they should be what? Very similar, so let's do that. I'm going to graph y equals negative 10x. Was it minus 25? Was that the? Yeah. Okay. Now, looking at the function, when I plugged in negative 5, I got out 25, so that's the point I'm looking at. So I need to adjust my window here and go over to the wrench. I only care about what's going on near negative 5, so I don't know, like negative 7 to negative 3 or something. And I know that my function value at negative 5 is 25, so that tells us about where to put the y's. You follow? So I don't know, 20 to 30. Boom, there it is. Does that seem to work? As you get closer and closer to this point on the curve, can you tell the difference between the curve and the line? No, that's local linearity. We found the tangent line. Okay. Let's look at what's going on near 0. So on the graph, when you plug in 0, what do you get out? 0. Take that off. Right, the graph goes through the origin there. And let's zoom in on that. What kind of line is that? It's a horizontal line, right? Horizontal lines have what for their slope? 0. Well, let's check it out. Y equals f prime of a times x minus a plus f of a. Let's look near 0. So y equals f prime of 0 times x minus 0 plus f of 0. I know my f of x is x squared. So my f of 0 is what? 0. I know my f prime of x is what? So what's my f prime of 0? So now I plug these in, I got 0 times x minus 0 plus 0. What do you get, folks? 0. Y equals 0, aka the x-axis. So when the derivative is 0, that's where things flatten out locally. You follow? And that's going to be an important concept for us moving into the next, well, not next week, but like the week after, because that's going to help us figure out where things flatten out. And that'll correspond to like maximums and minimums and things like that. Okay. All right. There's a couple other tangent lines for you. There you go. Example 2 is a video. It involves a fraction. Okay. Now, spoiler alert, when you go through this limit, it should look hauntingly familiar because this was a limit back from section 2.3, one of the video examples we did, ends up actually being this limit. So if you have deja vu, good for you. So once again, you know, how you use these worksheets and stuff is up to you. But if I were a student, what I would do is I would try working this on my own first and then fire up the video. If I get the answer, okay, great. If not, I'd fire up the video, scroll through it or watch it. A lot of students say they'll watch it at double time because I talk much slower on the video. But whatever. But once again, as your instructor, I expect you to engage with this example somehow. You follow? Example 3. Once again, it's a video. This is the position function we had from yesterday, where we went through and found the velocity when t equals 15. In this one, you're going to find a formula for the velocity that'll work at any time t. And you've got some analysis there for that. Okay, once again, as I mentioned, you know, this course is called Calculus with Analytic Geometry. So that means that, excuse me, you should have pictures in your head for all of these concepts, all right? And they should help you work together. Or the algebra should work together with the geometry to help you with the concepts. So I'm going to just get a copy of the worksheet here. Let's take a look at this. First question they ask, is f prime of 2 positive or negative or 0? How do you know? Okay, so once again, here's the graph. And you can bet dollars to donuts there's one like this on the test because I love these types of problems, right? So f prime of 2. So first off, we have to remember what f prime of 2 represents on the graph. F prime of 2 is the derivative at 2. So what does that mean on the graph? I'm looking for the what? The slope. So I come over here to x equals 2. This gives me the y value. So to be clear, f of 2 is the y value, which is 0. But f prime of 2, that's your slope. So if I imagine the slope there, I think about the little linear piece there. And looking at that little linear piece, is that line increasing or decreasing or flat? It's decreasing, which means the slope is what? Negative. So f prime of 2 is negative because locally we have a decreasing line. Does that make sense or not, folks? Now it asks us about f prime of 3. Is f prime of 3 positive, negative, or 0, or how do you know? So once again, f prime of 3, I'm looking for the what? Slope. So I go down, I go over to 3, go down to the curve. Negative 5 would be f of 3, but I'm looking at f prime of 3. So what do you think the slope is there? 0. It looks like the slopes are negative and then they change to positive. So the slope here is 0. So f prime of 3 is 0 because it looks locally what? Locally horizontal or locally flat. Make sense or not, folks? Which is larger, f prime at 0.4 or f prime at 0.8? So come over here. Here's 1. So 0.4, 0.2, 0.4 would be there. And then 0.8, 0.6, 0.8 would be there. So I come up to the curve and I kind of rough in the tangent line at those 2 points. Which one's bigger? Well, we're looking, when we talk about bigger, we're looking at the slopes here. So which slope is larger and why? Yeah, the one at 0.4 is larger because it's steeper. You follow? So so first off, f prime at 0.4 and f prime at 0.8 are both positive. And then the curve is steeper at x equals 0.4. So that means that the derivative at 0.4 is bigger than the derivative at 0.8. Does that make sense or not, folks? Okay. Once again, differentiability, locally linear. And now it asks us to use interval notation to describe the values of x for which f prime is less than 0 and bigger than 0. So f prime of x bigger than 0, that means we're looking for what kind of slopes? Positive slopes. So let's look at this here. Now technically speaking, I mean this is a technicality, technically speaking the derivative is defined coming in from both directions. Right? So often what you'll see is when they talk about these intervals, they'll just list them as open intervals without endpoints. Right? So but it's a technicality. But starting off here, you can see that the function is always rising. All of these slopes here are positive. So the derivative would be positive from 0 and 1. And notice these are x values. So coming along here, from 0 to 1, we've got positive slopes. And then at 1, what's the slope? 0. Then the slopes turn what? Negative. And they're going to stay negative until what x value? 3. So then f prime of x is less than 0 from x equals 1 to 3. Once again, these are x values. And then at 3, it zeroes out again, and then they start to do what? Increase from 3 to 4. You follow? Make sense or not, folks? Okay? So a problem like this on the test, if you get the concept, doesn't take that much time. You with me or not? You just got, but it's the understanding what the derivative is geometrically and then explaining yourself. You follow? All right, number 5 is a matching game. Match each of the function on the left with the graph of its derivative on the right. So let's think about, for example, the first one here, f of x. Once again, thinking about f prime of x here, f prime of x, these slopes are all what? So these slopes are all positive, and then this slope right here is what? 0, and then these slopes here are all what? Negative. So which of the graphs on the right are positive, 0, then negative? Yeah, graph B. So here we've got the y values here. So this would be the graph, once again, of the derivative. All of these are positive, indicating positive slopes. Then it's 0, and then it's negative. You see the connection or not, folks? Okay. Now what about g of x? All of these slopes over here are what? Yeah, these are all negative. Then it's what? 0, and then it's what? Positive. So which graph has negative, 0, then positive? Graph C. You see the connection or not, folks? So now by process of elimination, we know that H must go with graph A, right? But can you see why? Because what kind of thing do we have over here? This is a what? It's a line, right? So whatever the slope is here, it's the same, and it's what kind of number? Negative. So this is a constant negative slope. And then on this side, it's a constant what? Positive slope. So do you see how that's graph A? Now here's a question. What's going on at 0? At 0 on the derivative, we have a what? What did we call that from last week? That's called a jump, right? So the limit there doesn't exist. Do you see why? We go from a constant negative slope, and then all of a sudden we turn around and go to a constant what? Positive slope. This thing is called a corner. And h prime of 0 does not exist because the slopes are different from either side. Make sense or not? So here's an example where the derivative doesn't exist. The function is continuous. It's a nice continuous function, right? You can draw it without picking up your pen. But differentiable, it's not, because it's not locally linear. So what kind of function is this? Like if I said, come up with a formula for that function. What functions have graphs that look like V's? Absolute value. So let's fire up an absolute value and talk, because we'll talk about this a little bit more here in a minute. Let's fire up absolute value. So you saw with x squared when we zoomed in, it flattened out, right? So let's look at absolute value x. There it is. Now what happens when I zoom in near the origin here? Let's put that up there. Here we go. Zoom, zoom, zoom. Does it ever turn into a line? No, it's a vertex all the time. You with me or not? It's not locally linear. You follow or not? That means it's not differentiable. Look at these are crazy. These are chemistry numbers right here. These are chemistry numbers, right? Or at least physics. I forget. Chemistry get really big. Yeah, I think concentrations are small in chemistry, but the number of things is big. Let's take a look here at example 6, same kind of a thing. What's going on here in f of x with graphs? With slopes. All of these slopes are what? Negative, but they're getting what? Steeper and steeper and steeper. You with me or not? So like it's like maybe like a -1, then like a -5, then like a -10. They keep getting steeper and steeper and steeper. On this side, all the slopes are what? Positive, but they're getting what? Steeper and steeper and steeper as you get into the origin. So which of these graphs here on the right shows that? Graph B. If we look at graph B, everything over here is negative. That corresponds to the negative slopes. But these slopes are heading down to what? -infinity. You follow? Because the graph is looking like it's trying to be vertical there. And then on this side, things are going up to what? Infinity. So this is what we call in the business, we call this a cusp. We've got plus or minus infinity slopes. We got one side going to -infinity and one side going to positive infinity. So they're mismatched, and that creates a cusp. A cusp is kind of like a black hole. It's like a singularity. A corner is a corner. You come in, you bounce off, you go on your way. A cusp, you don't leave. It's continuous, but on either side, you're getting these infinite slopes of different characters. So a classic example of this is the what I call the bird function. So I call this the bird function. So we'll talk about why I call it that. Because children tend to do this. I don't know where they pick it up. This is how children draw birds in the background. When they're asked to draw, isn't that how they draw birds? I guess that's what seagulls look like. I don't know. But then the weird thing is, like, everyone does it. It's like my in-laws, my sister-in-law and brother-in-law, they literally took my nephew and the family to Disney World because all the kids, I guess, were going to Disney World. It's like that's a lot to do because everyone else is doing it. I've never been to Disney World. I'll never go to Disney World. Even though they have a life-size Millennium Falcon, which you would think would be the first thing, I would never go. Because as an adult, I'm a cynical person, and I know how Disney World would be if I went there. There'd be tons of people everywhere. I'd have to mortgage my house. Well, let's start zooming in at 0 here to observe this cusp. So once again, a cusp is when you have one side, the slopes are going to -infinity, and the other side, the slopes are going to positive infinity. So it's kind of like a black hole. You just get sucked down in there. Okay? And it's so steep, you're not going to be able to get out. The function is continuous, though. You can draw it without picking up your pencil, but it's not locally linear because of that funneling effect. And I'll let you think about G and H. Because if you pay attention, and we'll talk about this next week, the same graphs appear over here for G and H. So I'll let you think about that. All right, once again, this is, I think this is the second time we've seen this kind of a thing, right? It's so important. I put this on your take home as a fill in the blank. All right, local linearity. So, how do we make this precise? So let's go back to the definition of derivative that we talked about yesterday. So the idea is if x is really close to a, then f prime of a is really close to f of x minus f of a over x minus a. Does everyone agree with that? That's what limit means. Limit means as x goes to a, if that's the limit, f prime of a, then that means that the thing inside, the slope of the secant line, is going to look pretty much like the slope of the tangent line as long as you're close. Does that make sense? Now, from here, you can sort of multiply both sides by the x minus a. And then you can add the f of a over. And so yesterday, this is what we were calling L of x, the tangent line, and that's what we were calling f of x. And so that's local linearity expressed sort of algebraically. You follow? And that's kind of where it comes from. Now, there's a way to actually codify this even more precisely. And that's the local linearity theorem. So here's what we do. Here's the theorem. If f is differentiable at x equals a, then there is a function epsilon of x. Now, we saw epsilon on Monday. Epsilon usually stands for some kind of error. You follow? So, to replace this approximation with an equals, what we do is we tack on this error term. So to be differentiable means locally linear, but it really means that you can write the function as the tangent line plus this error term. And what is this error term? Well, the error term is essentially the difference between the slope of the secant line and the slope of the tangent line. And then we'll define it to be 0 if x equals a, because if x equals a, the slope, the tangent line and secant line are the same. So really all this epsilon thing is it's the slope of the secant line minus the slope of the tangent line. So I have a video on this where I go through and prove the theorem and go through all the things. Once again, the proofs of things at this level, you should get comfortable with the ideas first and then engage in the actual proofs. The proofs is where the math happens. Okay. Now here's the thing: you're not going to see this in any. There's no textbook I've seen in teaching calculus for 30 years that actually presents this result in Calc 1. The reason I do is because it makes a lot of the proofs a lot easier and justifies a lot of the arguments we're going to have, not formal proofs, the arguments we have that shows you why these properties work, right? Because I'm all about not only showing you how the stuff works, but why it works, right? That's kind of what makes this a sophomore level mathematics experience. There's the why behind it, okay? A lot of folks come into this class thinking mathematics is like 10,000 different rules that don't have any connection. I'm really trying to show you how all these ideas are connected. The other reason I like to show you this is because how many of you need to take multivariable calculus at some point in the future? At least a few of you do. This is how they define differentiability in multivariable calculus when you have more than one letter running around. Okay? Because having slopes exist in 3-space ain't enough to guarantee local linearity. You need to have something else, and this is the something else. Okay? So once again, practice, do the other things on the handout, do the homework, come back to this proof. I have it written out here for you. Right? And this, once again, this is one of those Carl's labors of love that I think this is something that's going to be unique to this experience. All right, we're off to chemistry today. What do we got going on today? What do we got cooking today in chemistry? Which one? Kinetics. Well, there you go. That's rate law stuff, right?
Yeah.
That's derivatives. So just ask him, what do you mean integrated? What's that integrate mean? Because that's a calculus thing that will be.
You mentioned taking the class to understand why they integrated.
I've had students, their final, we don't do projects over the summer because we don't have time, but several students over the years, their final project in Calc 1 is deriving the integrated rate laws from chemistry. So there's calculus there. So once again, just say, well, I wish I could have stayed in calculus instead of coming over here. All right. Now we're going to talk more about, for the last half hour or so, we're going to talk about the connections, differentiability, when it works, when it doesn't work. So we have two types of properties for functions that we've talked about. So we have a function f. We have the concept of continuous, and we have the function of differentiable. Okay. Now we have a nice geometric understanding of what continuous means, and I've mentioned it already. Continuous means that when you're drawing the graph, you don't need to pick up your pencil at all, right? So if you're continuous at some value, let's say a, whoops. We'll call that f of a. If you're continuous, then that means that locally the graph looks like that. You just come in there like that. Differentiable means locally linear. And so that means when you zoom in far enough on the graph, I don't know why my stylus always freaks out. Not only, I mean, it looks like a line, you follow? Now, if you're locally linear, then that means that locally you look like a line. That means you're going to have to be what? Continuous. So if f is differentiable, in other words, locally linear, then f has to be continuous. Does that make sense or not, folks? Okay. Now, the formal proof of that runs something like this. To be continuous means that as x approaches a, f of x approaches what? You can get the limit by plugging the number in, right? So if that's true, another way to think about that is that if I look at the difference between f of x and f of a, that has to go where? 0. So if f is differentiable at x equals a, f is locally linear at x equals a, so f of x is roughly equal to f prime of a times x minus a plus f of a. And so f of x minus f of a is roughly f prime of x times x minus a. And so what happens as x goes to a? Well, what's going to happen over here? Well, f prime of a, I mean. As x gets close to a, this is some number. This is going to where? 0, which means this is going to 0, which shows that the function is continuous. Make sense or not? Now, the formal proof, the capital F formal proof, once again pulls out this epsilon again. And you can see what it does there. Okay. So we have a if-then statement. So if f is differentiable, then f is continuous. So this is a logical construction called a conditional statement. Anyone take logic at all? So logic is kind of like the backbone architect of how mathematicians frame their arguments. Okay, so this is a conditional statement. All right, so I drive a gray car. Another way to say that is that if you find my car, then I'm guaranteeing that it's going to be gray. You follow? Does that necessarily mean if you find a gray car that it's my car? No. All right. So in this case, there are continuous functions that aren't differentiable. And we've seen a couple already. The bird function, the absolute value function, those are continuous functions that aren't locally linear. You follow? So if you think about, you've got this ocean of functions. Within that ocean of functions, there are a special class of functions continuous, because we know that not all functions are continuous, right? We have discontinuities. And then within the specialized set of continuous functions, we have even more specialized functions, the differentiable functions. So let's look at what goes wrong analytically with some of these things. So for each of the following functions, show that f is continuous at 0. Use the limit definition, and once again, here's an example. I tell you what definition to look at to show that we're not differentiable, and then graph to see what's going on. Okay? So let's look at the absolute value function. We know that the graph has what we call a corner. And we zoomed in on that corner and we saw that it never leveled out. Let's see what happens when we try to figure out the limit definition of derivatives. Let's try to figure out what goes wrong if I try to find f prime of 0. So the limit definition we're using is this one. But the x value we care about in all of these examples is 0. So this will all be zeros. You follow? So f of x is the absolute value of x. What's f of 0? 0. What's x minus 0? X. Okay? Now, of course, look what happens. I've got an absolute value of x. X is heading into 0, and 0 is where the absolute value changes. You follow? So, absolute value of x is one of two things. It's going to be x itself if x is bigger than or equal to 0, or if x is less than 0, what's the absolute value going to be? Minus x, the opposite of x. So if I look at the limit as x goes to 0 from the right, I'm just going to put x in for the absolute value of x. And what's x over x? 1. Which hopefully makes sense because that's the slope for the positive x values. You with me or not? If I come into 0 from the left, I'm plugging in things less than 0, so my absolute value of x is going to be the opposite of x. And that is always what? What's minus x over x always equal to? Negative 1. And hopefully that makes sense because over here the slope is always what? Negative 1. So do these numbers match? So does the limit as we go to 0 exist? It does not exist. You with me or not, folks? So this is what they call a corner. A corner is what happens when you have two different finite slopes that don't match up. You with me or not? So corner, finite slopes, they don't match. That creates a corner. That's a sharp turn in the graph. It's not locally linear. Okay? Any questions on this example? All right, let's look at x to the 2/3 power. So this is that bird function we looked at. So once again, let's just see what happens here. At 0, f prime of 0 is the limit as x goes to 0 of f of x minus f of 0 over x minus 0. And in this particular case, f of x is x to the 2/3. F of 0 is 0. That's divided by x. And so what can I do with these exponents here? I've got the same base. They're being divided. So what do I do with those exponents? Subtract them. So we get x to the 2/3 minus 1, which is x to the minus 1/3. And if you have x with a negative exponent, that really means that the x belongs where? In the denominator. Okay? Now let's remember that x to the 1/3 power is really the what root of x? That's cube root. And we're coming into 0. So we're plugging in small numbers. So if I look at the limit as x comes into 0 from the left of 1 over x to the 1/3, I've got 1 over a small negative. Let's do this on the next slide here. So as x comes into 0 from the right, 1 over, I got a small negative to the 1/3 power. So I've got a small negative that I'm taking the cube root of. If you take the cube root of a negative, what kind of number do you get? Negative. If 1 over a small negative is going to give me what kind of number? A big negative, so that limit is going to be what? Negative infinity. But on the flip side, x is coming into 0 from the right. I've got 1 over a small positive to the 1/3 power, which is the cube root of a small positive. And if you take the cube root of a positive number, it stays what? positive. 1 over a small positive is going to give me what kind of number? Big positive. So this is going to what? Infinity. And so this is what causes, once again, we call this thing a cusp, because we've got slopes going to minus infinity and then slopes going to positive infinity. Oops. So if on one side you've got slopes going to minus infinity, on the other side going to infinity, then you've got these infinitely, you created an infinitely steep well. You follow? And that's what we call a cusp. Make sense or not? Once again, you want to think of these are slopes. You with me or not? So these are the slopes, and the slopes are going to minus infinity one way, positive infinity the other way. That creates that well. Now the last kind of thing here we want to talk about is the cube root of x, which as a power, this is x to the what? 1/3. And let's take a look at what's going on here at 0 for the derivative. F prime of 0 equals the limit as x goes to 0, f of x minus f of 0 over x minus 0. And once again, I can subtract the exponents here. If I take 1/3 minus 1, that leaves me with x to the minus what? 2/3 power, which once again I can think of as 1 over x to the 2/3. Now, here's the difference. If I look at x to the 2/3, I still have the cube root of x for that denominator, but that numerator says I'm doing what? Squaring stuff. So, does it matter if I come into x from the left or right? If I come in from the left, I take the cube root. That keeps it negative, but then I turn right around and what? Which makes it positive. And of course, if I start with a positive, I'll get a positive. Yeah, Owen.
Is the cube root of x squared the same thing as that?
Yeah.
Okay.
So, regardless of what I plug in for x, whatever direction I come into, I'm going to get a small positive in the denominator, which means the whole thing's going to blow up to infinity. So instead of having minus infinity slopes one way and positive infinity slopes the other way, causing that sort of that vortex there, here from both directions I'm increasing both ways. So let's look at what that produces. You might remember this graph from college algebra, I don't know. Let's graph x to the 1/3. And let's go back, hit the wrench, do the standard window first. And we'll zoom in. So you can see what's going on here. You see how all these slopes are going to be positive, you follow? They just get really, really what? Steep. And then all these slopes are positive. They just get really, really what? Steep. So they get steep from the same direction. So that produces slightly different behavior. This is what we call a vertical tangent. X equals 0. So in other words, there is a tangent line, but it's a vertical line that's the tangent line. Does that make sense? So if you have two finite slopes that don't match, that's a corner. If you have two infinite slopes that don't match, that's a cusp. If you have infinite slopes that match, that's a vertical tangent. So to be not differentiable, the first thing is you could not be continuous. Because if you're not continuous, there's no way you can be differentiable. You can't be locally linear if you have an issue with the graph itself. Does that make sense? Or you could have a corner. So you have two different finite slopes. You could have a cusp. So you have two different infinite slopes. So you got one going to infinity and one going to minus infinity. Or you could have a vertical tangent where you have two, or you have the same infinite slope from both directions. It means it's just really steep there. You follow? It's just really steep drop off. Okay. All right. So what we're doing tomorrow then, so there's your homework. So once again, engage with example 2 and 3. So work through those, watch the video if you need to. Work through the homework, as many as you need to feel comfortable with what you're doing. If you have time, watch the proof of the local linearity theorem.